Damping. An oscillating system will experience resistive forces due to friction, including air resistance. These forces will oppose motion and so will gradually reduce the amplitude of the oscillations. If these forces are small, the period of the oscillator will be unaffected. If we plot a graph of amplitude against time, we'd get something like this for an undamped oscillator. The amplitude is not reducing from one oscillation to the next. However, we'd get something like this if the system was lightly damped. We're losing amplitude on each oscillation. We might get something like this if the damping was heavier. Notice that in all these cases the system is carrying out several oscillations and the time period is not affected. With heavy damping, we might get a situation like this, where the oscillator doesn't quite return to its equilibrium position, or at least takes a considerable time to do so. So this would be the situation with heavy damping. Heavy damping does increase the time period of the oscillator. If the oscillator behaves like this, it has what is called critical damping. Critical damping causes the oscillator to come to rest in as short a time as possible without overshooting. A meter should be critically damped, bringing the needle to rest on the required reading as quickly as possible without oscillating about this reading. A car suspension system is also critically damped, and this is part of the MOT test. Damping is a problem in systems that are designed to oscillate continuously, such as the pendulum of a clock. In this case, energy is added on each swing to compensate for the energy lost. This energy can come from a wound-up spring, a raised weight, or from a battery and a motor.